Hello, and welcome to today's Micron Value Partner webinar, Big Data, Advanced Storage, and Other Fun Stuff. I'm Matt Wokus, Strategic Marketing Manager for Micron Storage, and I'll be your moderator today. Now, before I introduce today's presenter and topic, I just want to get a few housekeeping items. First, please feel free to submit questions at any time during the presentation using the Q&A tool on your webinar viewing screen. All the questions today until later in the presentation, and we'll ask them of our presenter as we try to, and we'll try to get through as many as we can. If you have to drop off before we conclude, remember this webinar is being recorded, and you can watch it on demand using the same URL as you used to log in today. And those archive webcast recordings are usually available just a few hours after the live webcast and are always used through the same link as you used to sign in. And, of course, if you're here with us live, you're automatically entered into a drawing for one of 3 crucial MX200 256-gigabyte solid-state drives. Tweaktown called the MX200 one of the fastest drives ever made, and PC World called the MX200 the most affordable top-shelf SSD out there. And today, at least for 3 of you, it will definitely be very affordable because it will be free. So anyways, we are pleased today to have with us as our MVP webinar presenter, Rob Peglar, who is Vice President of Advanced Storage Solutions for Micron. Rob joined Micron in February to lead the next generation technology and architecture enablement efforts with key customers, strategic partners, and potential new flash storage end user verticals. Rob's nearly 40-year career of leadership in the data storage industry has included key roles at EMC Isilon, Xiotech, Storage Tech, Network Systems Corporation, Control Data, and ETA Systems. He is currently a member of the Board of Directors of the Storage Networking Industry Association, SNIA, and has been named Storage Superstar by CRN. So today, as Rob is going to give us his view of the future of storage trends and technology, and how there's a paradigm shift underway, and how we look at data storage driven by the rise of big data. So Rob, thanks for joining us today, and we look forward to hearing your thoughts about big data, advanced storage, and other fun stuff.
Well, thank you very much. I appreciate the intro, and yes, you are correct. I have had a long career, although I prefer to state that in hexadecimal. So the record, it's 26. So you guys do the math.
I'll make a note of that.
There you go. Excellent. So I'll tell you what, I'll run through this material. I think you're going to enjoy it. I see there are several folks I already know on the attendee list. Thank you for sitting on the webcast, and for everybody else as well. I think you're going to enjoy this. There's a bit of history in this presentation as well, because I think if you don't understand history, it's difficult to understand where we're going to end up or where we're going as well, especially in storage. So I'll go through these slides, and then we'll get to a little different section as well, talk about some architecture, and then some future, as is said, very fun stuff. So Niels Bohr, the eminent physicist, once said, prediction is very difficult, especially about the future. He was absolutely right. So understanding the past, I believe, again, is important. And that drawing you see on the left is actually a blueprint. I put that in there for several different reasons. First of all, my father was a mechanical engineer, and he used blueprints to do his various projects. Now, of course, we have all sorts of interesting computer-aided design tools and electronic design, but understanding that was the data of the past. Now, we talk about big data quite often today, and sometimes it becomes a very ambiguous term. But I believe it's fundamentally different than we're used to, and here's why. So consider a movie, right? You and I have been to the movies. We observe the pictures on the screen, and they appear to be actually in motion, whereas fundamentally they're a collection of still photographs. So when you look at a still photograph, you certainly see an image, but it's not moving. There's no action involved, and it's a very different experience than seeing a movie. So I think that big data is much like a movie. We experience it differently. It comes in waves. It's very sequential in nature. It flows. It's not very, static, random, kind of row column oriented data. So a movie is much more than a collection of still photographs, I think. And that's one way to think about big data. So let's take a little trip into the past, the Wayback Machine, if you like, if you're a fan of that cartoon show. But what you see on the left is actually historically consequential in computer science. That was the original Hollerith card punch. And why is that important? Well, over time, we've had different documents that represent data that's important historically. For example, in the United States Constitution, if you're a citizen, you well know that there is this thing called the decennial census. That's a $5 word for every 10 years. So in 1880, when the federal government took the census, and if you can see these online, if you're a fan of genealogy, as am I, and use the websites to peruse your genealogy, you can literally see these documents. The census back then was handwritten, taken, of course, by humans going door to door, farm to farm. And then when it was all compiled, it literally took the federal government 8 years to collate all the information. Now, you can see the problem. They only had 10 years in which to do it because the 1890 census was coming up. So in 1890, they took a look and said, how can we process this data differently, much more effectively? It's the same data, right? Data on citizens in the U.S., where they live, who their family is, their occupation, all that data. But let's process it. Let's analyze it differently. So they hired Herman Hollerith, and he brought his punch card tabulator machine to bear. This was quite literally the beginning of automated data processing. And guess what? It only took the federal government 1 year to process the 1890 census. So this was one of the first key lessons in the application of technology to improve workflow or to improve data analysis. Now, of course, here we are in 2015, some 125 years later, and guess what? We're still applying technology to analyze data in more efficient patterns. So nothing new there, and that's why I wanted to make that link to the past for you. Because that order of magnitude, the difference they saw, 8 to 1, was fundamentally different than collating it by hand. So let's talk about sampling now. Now, on the left, another bit of history for you. Since Micron obviously is involved in the memory business, as all of you know, this is actually a picture of a Williams tube. This is circa 1946 in some of the earliest computers, and this held a whopping, and I mean whopping, 1,024 bits. Not bytes, not megabytes, not gigabytes, but bits. And it was quite expensive, especially for the time. So we've come a long way in memory. That's the bottom line there. Now let's talk about sampling. We all know that sampling is a statistical method to sample data, to get data collection, and then try to make some conclusions based on the sample. Well, 80 years ago or so, Jerzy Neyman from Poland proved that it wasn't really the size of the sample that was important. It was the randomness of it. So you can go back. I actually have the citation there. If you're interested, go back and read the paper. But the randomness of the sample was very, very important. You get a better sample if it's more random. Now, sampling, of course, introduces bias, and systemic bias at that. You can get the wrong conclusions, right? Like the old newspaper headline in politics, right? Dewey defeats Truman. So that was based on a bad and a biased sample. So the seismic shift really is now occurring in data where we're actually starting to gather as much as we can. Some people call this N equals all, and you'll hear me use that term in a little bit. So let's not just sample the data to keep it nice and discrete, but let's bring in all the data, take all the streams, take all the data sets that we possibly can, and analyze them on purpose, keeping the data sets large on purpose, so we can have a much more random, not necessarily small, but certainly random sample. And why would we do this? Well, if you're a credit card company, for example, you're trying to analyze fraud, the normal quote-unquote transaction really isn't that interesting. What is interesting is the outliers. So if you take bias samples or very small samples, chances are you won't see outliers, or you'll see very few of them. But gathering all the data, storing all the data, analyzing all the data with unstructured data techniques, that's where you're going to find the really interesting outliers, the really interesting exceptions. So as the bottom says, don't follow the rules, just look for the exceptions, and you're going to find some really interesting data points. Okay, this is an interesting slide. I'm going to tell you a little bit about the journey from what I call clean to messy. Clean data is that data which is known, it's in a schema, if you know your databases. It's very systemic. It's in nice, neat rows and columns. Even the location within the rows and columns is dictated by the schema. That's very clean data, typically usually vetted out months or even years in advance and kept in the same format. Messy data, on the other hand, is what we see today, for example, on social media feeds or data coming in from sensors. It's in a particular pattern, but it is certainly not organized in a static, structured way. So we have to apply different analysis tools. And in the last 5 years, we've gotten some really interesting tools. So I reference a person named Greg Linden, who happened to work at a Seattle startup that sold books online in 1998. Well, if you're guessing who that is, guess no further. That is a company we now know as Amazon. So he actually wrote a patent. You can, again, go look it up. I've got the patent citation there for something called collaborative filtering. And the joke is, although not a joke at all, it's very much to the point that Linden is quoted as saying, if it works perfectly, Amazon should show you just one book, and it will be the next one you will buy. Emphasis on the word will. So it's doing prediction, right, based on collaborative filtering. So that's one relatively early example, 1998, of a patent that's applied to the analytics of data. And we know it now. It's actually very ubiquitous now. We all go to these retail websites. They try to predict, hey, Rob, this is some book titles you would like. Or if you log on to your favorite, content streaming service, these are titles you may like. It all comes back to this particular collaborative filtering work and a lot of work since then. So we have now what I call datafication. Everything is data. We started way back when with numbers, right? Roman numerals, Arabic numerals. Numbers were data because they were the first things that were actually written down along with words. So words and numbers were the first pieces of data, but they weren't very widespread. Then when Gutenberg, of course, invented the movable type, movable printing press, then words became much more available to the ordinary citizen. So now we moved into a little bit of the past, and we have images as data. So again, still photographs, and then later movies. Those became data. Remember, still photographs and now video camera data can be analyzed, and there's all sorts of interesting techniques, in fact, to analyze that data. So imagery is now data, and it has been for probably arguably 20 or 30 years now. So again, from still photography all the way up to very sensitive now image analysis, facial recognition, pattern recognition in space, that sort of thing. Very interesting stuff. Now, the last three, locations and relationships and feelings, you wouldn't think ordinarily they are data, but with our friend the GPS, guess what? Locations are data. And if you've got siblings or children in their 20s, as do I, you know that GPS is now ubiquitous. We literally live with this now. GPSs are on our mobile devices, and they have been for several years. Location data is extremely important to lots of businesses and to us as consumers. I travel frequently, as many of you know. Quite literally, I don't think I could function as efficiently without location data. Where's the hotel? What's the best way to the airport? How do I get to my next meeting? So locations are data. And again, the retailers, the insurance companies, the banks, all these consumer-oriented firms are taking advantage of location data. And then lastly, relationships and feelings. This is not in an effort to be overly emotional, but guess what? We tell the world now, here it is 2015, and we tell the world now how we feel. The like button is actually aptly named. I'm actually still waiting for the dislike button on Facebook, but that's another story. But we are telling the world about our relationships. How do you feel about a particular product? Are you a fan of Coke or Pepsi? Colgate or Crest? How do you feel about a consumer product? How do you feel about, the last statement made by the U.S. Congress? All of that now is on social media, and guess what? It's data. We can pull in those streams. We can analyze sentiment analysis, the entire feeling of gauging sentiment using data. 20 years ago, this didn't really exist, at least in today's form. We had to take surveys on paper. We had to take surveys by telephone. And again, guess what? Those were small samples, and they were usually biased. Now we have these complete streams of data flowing in from all sorts of different outlets, and we can tell how people feel now about certain things. So there are some areas of computer science like graph theory with nodes and edges. It really is changing the way we perceive the world because of our ability to compute, and more importantly, our ability to store this data for the subsequent compute. So that's the journey from clean to messy. We are in the era of messy data, and I don't think we're going backwards anytime soon. So let's talk about the future a little bit. You know, data as policy. Since everything is data now, arguably, again, images, feelings, relationships, words, locations, we can now start to create policies around the use of this data. And there are some really interesting career paths and titles coming out of the woodwork now. I've heard of careers and titles called the data ethicist. So someone who studies the ethics of data on behalf of a corporation or a university or what have you. Data scientists are now well known. It's a great career. Lots of folks are starting to enter the data science field. Then there are other titles like data correlationist, a very important term because now data is mostly about taking correlations between data sets as opposed to trying to actually form causation from a given data set. So Deming had a cute little quote. It's actually true. In God we trust, all over there's bring data. So is knowing what good enough? In other words, what happened, what is likely to happen instead of the why, which is causation. Some folks say it is. Other folks say it isn't. It is an interesting application of the scientific theory to talk about things like what and correlations as opposed to causation. But remember Bayes 250 years ago with inductive probability. This kind of flies in the face of some of the things that we may have embedded on our minds, but this is a very hot area now of both study and in data analytics because Bayes said 250 years ago that we update our beliefs about something as new data arrives. So we can change our mind, we can change our feelings, and in fact the whole study here of Bayesian induction is very interesting, very applicable in the study of data analysis. And then last but certainly not least, I am from St. Louis, as many of you know, so I'm going to quote the St. Louis native Yogi Berra. Although he ended up playing for the Yankees and had a brilliant career, he was not selected by the Cardinals, unfortunately. But Yogi said two things. He said, number one, we make too many wrong mistakes. And I have to tell you, that is just a point you cannot argue. All of you do it. I do it. We make too many wrong mistakes. And then the second thing, which is very true, think about it in terms of data analysis. You can observe a lot just by watching. Phenomenal. So let's go back to the present for a little bit. I'm going to spend some time on this slide. I think it's very important. This is an architecture slide, kind of from left to right, if you like. But to me, it's a pretty good depiction of the world of data analysis, and especially that second part there called data acquisition, architects and engineers. And I am an engineer by trade, have been for a while, although in executive positions now, love doing that, still keep my hands in engineering. I think it's really important to do that. But that second part is where infrastructure plays a very unique role in the flow, kind of, again, from left to right. So starting on the left, all these producers of data, I talked about several of these sources now, and this, again, is radically different from when I started my career or even backwards in the past. Machine-generated data, transactions and usage logs. These are literally exploding now as we bring more devices on that have logging capability, and the storage and analysis of those logs is extremely important in data centers, small and large, in public clouds, in private clouds, in normal data center infrastructure. Fantastically important data to analyze. And then, of course, we all know the world of email and messaging, primarily the messaging world now. And then relationships and social influence. Like I said, these are the feelings and relationships that are becoming data. Mobile app data, that's a whole nother lecture for another day. All of you carry mobile devices and probably multiples of them. And along with geolocation, this is forming a new stream, or streams, I should say, plural, of data that quite literally 10 years ago really did not exist in any way, shape, or form. All this data is now flooding in. We need to acquire it, and we need to acquire it intelligently, and then we need to store it and then process it. And again, that's where that second box comes in. So all these little techniques that you see depicted on the slide, the scale-out storage, the world of Hadoop and non-structured analytics, non-relational data warehouses, non-relational databases, the so-called NoSQL platforms. But coupled with that, the new, actually old but new again, technique of in-memory compute, massive parallel processing, very high speed, very resilient networks to connect compute and data, and then last but not least, converged and now hyper-converged infrastructure. All of this now is blending together to form the substrate for intelligent data analysis. Again, both the storage and the compute of it. We absolutely need to store it, sometimes indefinitely. This is where the lawyers come into play. After all, the most popular retention period is, say it with me now, forever. And the lawyers make it so. But acquiring the data, storing the data, processing the data, really important, because the way you do that and the efficiency of that really drives what you can do to the right. So finally, on that third and fourth part of the slide, the depiction of where the data analysis, where the data scientists come in, applying all sorts of different models, all sorts of different forecasting techniques. A lot of data analysis today is not about, regressive or in the past behavior. What happened. We think we know what happened. Now we try to predict events. Again, as Niels Bohr said, prediction is difficult, especially about the future. So we're trying to apply these analytic techniques now to data in all sorts of different ways. Contextualized data, data modeling, different data scenarios, playing what if with the data. Again, all wrapped around stream processing, all wrapped around events. Events come in. They want to be analyzed sometimes in real time, sometimes not. But they have to be processed in different ways. And again, this is a wonderfully fascinating field of both study and practice now, data analytics performed by data scientists, and an ever-widening, I would say, group of people that are involved in the processing of this data. Because, guess what? Last but not least, you want to get to the right, the fourth column there, and get data that enables better business processes and more efficient end-user use of data. So how do you do it? How do you get data to the end users? Well, you can push it. You can do the so-called pull technique, represented as on-demand there, or embedded. And embedded data is really interesting because that puts us full circle back into the realm of machine-generated data and sensors, embedded data coming back to the sensor in a feedback loop, data coming back to your mobile device so you can see it again, or perhaps a little bit altered. Because of processing that's happened, hey, you're in location 2 now, Rob, not location 1. I'm going to update your map for you. So this is the value that's generated by this analysis of the data. So you can have better workflows. You can have better alerting and responding to events, or events that might happen, again, in a predictive sense of the word. So again, I've spent a little bit of time on that, but I think designing architecture to meet this workflow all the way from the creation of data, which is on the producers. Maybe your company is involved in highly efficient techniques to produce data. Maybe it's involved in acquiring it. From my point of view, being in the storage industry, acquisition, storage, processing of this data in a very efficient way is the area where I live. And then I have to tell you, when I see analysis and these new algorithms being applied, new techniques to data, it's just fascinating to see the end result and what can come forth from the analysis of this data. Okay, let's talk about that business value. So I'm going to flip through the slide here a little bit. Data is very, very valuable, as we know, increasingly so, and the reuse of data really is the key. Data is not just a single entity. It's meant to be reused. It's meant to be reanalyzed over time. If you're an economist, easy for me to say, this is called a non-rivalrous good, so data that's reused. There is such a thing called recombinant data, which is really older data or data that was gathered in the past, being combined with newly emerging data, newly arriving data, actually to provide new insight on a given problem. And then the concept of the noisy data set, enabling the feedback loop. If you've ever used machine translation, you know about noisy data sets, or actually maybe you don't, but they're in the background of these translators, because as the translator hears more quote-unquote noise and eventually figures out the patterns of that data, it becomes a better translation engine. So now let me skip back to that second bullet there. The cost of benefit of storage is approaching zero, so keep everything. That's actually one of the fundamental premises that I believe. I won't say it's dominating our thought today in storage, but it's beginning to, right? Keeping everything, N equals all. That doesn't mean keep everything forever, although, as we know, sometimes the lawyers make you do that. But keeping everything to further the analysis of data, at least for a certain time period. And there's all sorts of fields of study: bioinformatics, seismic processing, again, semantic analysis, A/B testing, that benefits from these very large, albeit unstructured data sets. And in the last 50 years, the cost of storage has decreased a half-fold every 2 years, or double, or 1/2 every 2 years. And then the density has increased 50 million times, quite literally, on magnetic media since 1956, when, by the way, that was the introduction of the first hard drive, was 1956. So business value of data, really important. So let's go into the future a little bit and talk about keeping everything. N equals all, and I have lots of folks say, geez, Rob, are you serious about this? We can't afford it. We just can't keep everything. There's no way we can keep up with the inflow of data. Even if we wanted to store it all, I don't think we could. Well, I would think that that philosophy, and along with emerging technologies like Hadoop file system, for example, it really presents a crisis for us, not only in the storage industry, but also in business. It's a Weiji, right, the two Chinese characters. It's really sometimes translated as dangerous opportunity. It's a better translation, as I learned, called critical point, a Weiji. So we are at a critical point. And keeping everything, keeping all data sets is a very difficult thing to do. Now, density helps. Reducing cost over time helps. But what really helps is to think about, should I move this data set or not? And when I say move, I mean physically from one place to the other, or in terms of transmission. Do I have to replicate it to another array or replicate it to a different server, that sort of thing? Because let's face it, time is not your friend when you're moving data, right? The data over very, very fast and efficient networks, very, very different than some of the media now, especially rotating media. And it is quite rapidly becoming a game about how fast can you transmit data, not only from place to place, but literally from the origin point of the data, where you have it stored, the persistent store, to the CPU, or more importantly, multiple CPUs that are going to process this data. So think about for a minute, how long does it take you to move a petabyte of data at 1 gigabyte per second, which is a fairly healthy rate? Well, long story short, answer is that would take you 11 and a half days or thereabouts. That's a long time. Even for a batch subsystem, that's a long time. And I know firms, and you probably work at them, that have many, many tens, if not hundreds of petabytes of data. And then again, trying to move that around just because you have to becomes a game that you just cannot win. This is time versus space, right? It is becoming more important in analysis to save time, to do more timely analysis versus the cost of space, which again is driving toward a lower point as time goes by. And the benefit of having that data is actually rising. So this is why I made the argument the cost-benefit ratio is actually driving rapidly towards zero. It'll never get there, of course. This is Zeno's paradox, right? But the cost of not having data, I would opine, is becoming much, much more significant than the cost of actually having or storing the data. Okay, so this is where we come in. This is a little bit of technology. Now that we've gone through the past, present, and future of data analytics and kind of the why and the philosophy behind the data, let's talk about technology for a bit. What is depicted here, I think those of you that perhaps work for my company, Micron, and maybe some others as well, have correctly figured out that this is actually a NAND flash cell. So if you're not familiar with the diagram, there you have it. That is NAND Flash 101. So this is where we come in. So let's talk about the storage, at least in terms of solid-state storage for a bit. Back almost 7 years ago, there were some predictions that used this kind of cute phrase, I'll call it, called flash and trash. That this was the world that the storage industry would evolve into, that almost everything would be held on flash, and then what was not held on flash was held on very slow, very dense magnetic media. Now, there are alternatives, of course. Optical transmission certainly is making a bigger play in the market these days. We know about optical media. That's kind of been phasing out for a while. But flash and trash is actually becoming very true. We are, talking all sorts of customers and prospects as well, and kind of there is a consensus now in the industry that the fate of the fast rotating drive is maybe coming toward an end. I won't say it's at an end, but maybe it's coming toward there, and we will start to enter the world of flash and trash. So let's talk about memory and storage for a bit. I'll tell you what, for what I see in the industry, those lines are blurring very quickly. There are all sorts of interesting non-volatile memories technologies under development that can be used like memory, that can be used like storage. So memory is storage and storage is memory. The lines are blurring very quickly. And if you went to school in approximately the same time frame I did, you learned about John von Neumann and his model of what a computer system should be. He had the CPU, the central processing unit, after all, in the center of the diagram. Everything else was around it. I would opine today that actually the data is now central, or what we used to call peripherals, right? That held data. Data is now central, and we have all this really interesting compute revolving around the data. Because after all, again, you don't want to move data too many times. It takes a long time to move a lot of data. So let's land the data once, land it on a highly efficient platform, and then compute off of that as quickly as possible. Okay, a little bit of hierarchy of innovation for you. I show this slide only because I want to draw a parallel to what you may recognize as Maslow's hierarchy. And again, if you went to school around when I did, you probably learned that, or maybe even later. But this is the hierarchy of innovation, if you like, and I turned it to represent, survival and social organization, kind of moving up the chain. Well, as it turns out, not just Micron, but other flash manufacturers as well, we are involved in actually the upper 4 layers of all of those technologies. If you think about it, architecture and government, for example, large consumers of flash media, the technologies of prosperity, we all know about, right? New manufacturing, new transport, new forms of energy. These are all using storage and, more importantly, data analytics. And then the technologies of leisure, the mass media, consumer goods that we all like, our handheld phones, our travel. This is chock full of technology and really enabled by flash technology as well. And then finally, the technologies of the self, kind of doing things like managing your own identity, right? Things that have to do with you and just you and the application of technology therein. So all the way up that kind of food chain, if you like, the hierarchy. There's innovation occurring at every one of these levels. And again, probably outside the technologies of survival, the upper 4 layers are now dependent on technology and, more importantly so, very innovative flash technology and solid-state technology that companies like Micron are putting out into the market. So here's a slide on social media. This is no news to all of you. I call this the new Gutenberg, right? I think the impact of social media may be, looking back in history, hundreds of years from now, as important as the impact of actually the printing press, because this is a fundamentally different way to communicate now with a handheld device. So yes, indeed, we are now in the era of Dick Tracy, but you can see the numbers for yourselves. I won't bother to read them, but just the proliferation of mobile and handset type of devices, and then the accounts and the providers that we use to enable social media, to allow us to communicate back and forth, to allow us to post our pictures and our videos, to allow us to express our sentiment about various things, all the way from very short burst text messages and 140-character Twitter feeds all the way up to very, very long blog posts and whatnot. So social media, again, there is no turning back from this, I think. And what's enabling all of this is memory products, especially memory for the handheld devices, memory for solid-state drives, memory for the long-term storage in the future of all of these images that, of course, we like to post and we like to trade amongst ourselves. So this is going nowhere but up in a big hurry. So here's some interesting vertical markets. So we know about lots of these, but they are becoming more interesting with the application of flash technology, I think. We all know about Hadoop and its large ecosystem. There are a number of analytics companies. There's Splunk, who I had the great fortune of working with in the past and even today, log analysis, things like that. And I just list some of these companies as a small example of the companies that are involved, and they are literally coming out of the woodwork. The world of analytics is being funded very heavily by the venture capitalists and by angel startup investors. So this is broadening out in a tremendous way, even as we speak. There are all sorts of now techniques for non-structured databases, the so-called NoSQL. Again, I mentioned some companies there. And then finally, there is the area of what we call in-memory compute. It's almost an oxymoron. I'm actually trying to find some out-of-memory compute, but I think I know you know what I mean. In-memory compute is what we used to do back in the days in the 60s and 70s when we didn't have virtual memory. You had real memory. You had real programs addressing real memory, and that was that. Guess what? This is back to the future. We're kind of back there again, where doing everything in memory, or as much as you can, is very, very important. There are entire database suites, massive parallel processing. They're all headed that way, if not there already. In-memory is rapidly expanding, pun intended. And again, it is companies like Micron that is facilitating this with memory products. But again, be that as it may, you are going to see, in my opinion, a huge increase in the use of in-memory techniques, especially applied to analytics, but not only so. There are all sorts of other interesting applications and algorithms that can be tuned and tailored to run directly in memory and basically read all the information in once and then begin to compute. So those are really interesting to me. And here's some more interesting vertical markets, again, kind of widely described. We know about the world of HPC and the national labs, petaflops and exabytes, but I have to tell you the commercial world for HPC is rapidly approaching that. I have seen firms left and right all over the world that are now standing up these very large compute clusters, tens of thousands, if not hundreds of thousands of cores, petabytes of storage, and petaflops and exabytes is where we're headed, no question about it. And then I'm going to jump to the last one. You know, again, the whole idea of wearing a camera on your person, be you a public employee, a civil servant, or just you and I, out there having fun and skiing down the mountain and filming it while we're doing it. The explosion, literally, of data coming from that in state and local government, in, for example, port authorities that are filming 24/7. There is just an amazing amount of video surveillance going on now, all enabled by efficient storage. And then again, down from the relatively small, minute flash devices that might be carried in a miniature camera, all the way up to very large archives for video data, all being enabled more increasingly over time by flash storage. So I've come to the stopping point here. It's about 40 after the hour. Hopefully you have enjoyed the little tour through history, if you like, with big data. I just find it fascinating as a storage industry person and as an engineer to kind of see where we've come from, seeing where we're going. There's all sorts of really intriguing and interesting applications of flash storage, or more importantly, solid-state storage in many forms. NAND flash actually happens to turn out to be just one of them. But the importance of higher speed DRAMs, we are now into the world of DDR4, of course, as you well know, especially if you're involved in infrastructure. All sorts of non-volatile memories on the horizon, all sorts of improvements in NAND flash, including 3D flash, which has been previously jointly announced by Intel and Micron. So the world is getting just really, really interesting when it comes to storage and analytics of data that is using these persistent stores. So at this point, I'll stop. I think I'll toss it back to you guys, and maybe we'll have some time for some Q&A.
Rob, thank you. Yes, I think we do have some questions that came in on the line. In fact, actually, I want to invite all the people that are still on the webinar, if you have any further questions for Rob, to use the Q&A window that's on your little presentation setup. So the first question we have is someone want to ask, why is, I guess, in-memory so important to the customer, in-memory storage or in-memory compute?
Yeah, that's a great question. And again, I'll relate it to my own experience. So when I started my career, in-memory was all you had. There was no concept of virtual memory. So a lot of programs had to be very tightly structured to not only read their data into memory, but make sure they kept that data there. And there was no inherent assumption that I had this gigantic virtual memory space to deal with. So that was the world of real memory, again, many years ago. Today, the technique is actually absolutely the same, and here's why. The difference in processing power and speed between, let's say, DRAM, and then going all the way out, especially if I have to issue an I/O, a read or write through a channel protocol and get to a device at the end of a channel, be it SSD or rotating, but let's say it's rotating, is just enormous, hundreds of thousands of times slower than actually accessing that same piece of data. Let's say it's a 64K block of data. It's either in memory or not, and the question becomes, how fast can I get it there? Well, if you're doing data analytics, especially real-time analysis of data, you quite literally don't have any time to wait. So what has happened is the technique that actually originated, again, in the HPC world where I started years ago, of reading as much data into memory as possible, consuming as much real memory as possible, and then using that space literally as a data repository, but an extremely fast one where the CPU can get to any piece of data that it needs. So skillful application development, reading in the data before I need it is actually very, very important because it literally saves thousands and thousands and thousands of, order of magnitude trying to get out to a piece of data that might reside out of channel and take, 10 milliseconds to retrieve, whereas I really want to read it in order nanoseconds from a CPU directly in cache, or the next step out is DRAM. This is really important, again, because of the pace, the speed at which we want to analyze this data, and then again apply it to our own techniques. We all use search engines. We'd much rather see a search hit happen as fast as possible than wait even a few seconds to get the result. Ergo, now I want to do much more in-memory compute than I could otherwise even just 5 or 10 years ago.
Yeah, that makes sense. You want to have it memorized versus trying to look it up.
There you go. Yeah, lookups can get really expensive. And again, think about, petabytes of data and trying to, determine, okay, which terabyte or two is really important. I want to bring all that into memory and analyze it as quick as possible. So that whole flow, again, and keeping memory saturated, keeping the CPU busy, because I guess I have news for you. You might as well keep the CPU busy because you paid for it, and you might you don't want idle time on that asset you just paid for. Keep it busy.
Another question here. So there's been a lot of talk about object data these days. So what's the challenge customers are facing, and how's that different from today's storage solutions?
Well, I'll tell you what. Object storage is actually not a new thing. It's really about, number one, how the application, and I'll use this word kind of improperly maybe, visualizes the data. How does the application expect the data to be organized? An object is actually a very handy way to represent data because it's literally a blob, and that's also an acronym, right? Binary large object. It's literally just a chunk, I'll use another word, of data, which once read in, now can be derived as to what the metadata is, what does this object represent? And then further, now, once I know the representation of that, because I read this 128K object in, it's, oh yeah, that's a photograph. Okay, now I understand. So the difference is, in today's world with these very powerful CPUs and cores, the host or the CPUs can do that in a much more intelligent way than, for example, 10 years ago, where object storage was relatively unknown because we didn't have the CPU power that we had today, so we had to have the storage device itself keep the representation of what that was. Object storage means there's a database or a mapping of some kind going on. Same thing with a file system, by the way. I have to map a representation of the data to where it's physically located. Object storage does the same, but the physical representation of where it's located is actually a very simple thing. It's quite literally, in some object storage, an address. So I can go fetch that object, and now it's up to the host to determine what it has. It consults the database, yet another reason to have that in memory, and then figures out what the object is. And the transport of objects can actually be very efficient. I can read in objects which are megabytes, even gigabytes in size, all in one fell swoop, and then begin to analyze that. So it's not necessarily the storage media itself. Some people conflate that, object storage means rotating drives or object storage means solid-state drives. It doesn't mean that at all. It's a way to represent the data. And again, I have a mapping of what it represents to where it resides on the media, somewhat similar to a file system, but file systems typically have human-readable things like a name and a directory, whereas an object store might have an identifier, maybe it's an integer, and then a container or a bucket, right? Which bucket is this object in? Which container is this object in? And it's, again, a form of addressing, but at its heart, it's a much more simple way to address a set of data, a certain amount of data, and then determine its representation. And again, this is leveraging now the power of the host. I think the pendulum has swung now toward the host being very, very efficient and the storage devices being very accessible to the host. We all know about PCI Express. We all know about NVMe. We can have storage that is, in compute time terms, quite literally very close to the host, and now starting to scale up that as well. But that's really what object storage is all about. It's a different way to represent the data.
Okay. Oh, you have another one here, and then this kind of ties in what you were just talking about. Now that
Sure.
Flash has really sped up the persistent layer of disk, is network becoming the bottleneck?
Well, I see that's from my buddy Dave. Dave, thanks for the question, and I would answer in fact, it is. This is we all in the especially in the storage industry, we all if we're concerned about performance, we play the game of chase the bottleneck, and it's kind of like whack-a-mole, because when you reduce the bottleneck to zero in one place, guess what? By definition, it's going to start to appear in another place. So you're absolutely right, Dave. We have very fast persistent storage today, accessible in tens of microseconds or even lower. And then I'm not even talking about the whole world of non-volatile memory, but just flash SSD, for example, on a PCIe with NVMe transport. So very, very fast response time, very low latency. And guess what? The networks are indeed becoming a bottleneck. It makes little sense to put a very fast device at the end of a very slow network, or in relative terms. So you have these devices transmitting or capable of transmitting at multiple gigabytes per second. You are now seeing the advent of 40 and 100 gigabit Ethernet, which I wouldn't call it ubiquitous today, but it's going to be there, especially 40. Micron, for example, just demonstrated transport and filling 100 gigabit links. Never mind 10 gigabit, but 100 gigabit, because that's the inherent nature of transporting devices which are that fast and have that high throughput capability. So networks are going to be increasingly important, or to your point, Dave, you're right, they will become the bottleneck over time. But the good news is I think the world of transport and networking is keeping up with the pace. There are some very efficient transports out there now. And then guess what? Again, our old friend optical transport is making a big comeback, certainly within a server, but now in between servers as well. There are memory-to-memory techniques, RDMA, Rocky transports like that, which I think are going to grow rapidly in the next year, 2, 3 years for sure. Mostly around, again, the ability for a given persistent storage device The whole game is how fast can I get that through the CPU to begin processing. Or, on the other hand, I've got a full memory and I want to put it back to the persistent store. How fast can I drain that volatile memory out to the persistent store so I can read some new stuff in so I can continue computing?
Great. Yeah, we have actually a couple of questions on just your thoughts about the future of Flash. There's been analyst firms have said there's not enough capacity to meet the data demands. How far does Flash get us today, and when does this change? And also, where do you think Flash will evolve to? Is it going to be more? Is it going to evolve more to more storage, more terabytes, or more performance?
Let's see. I'll take the last question first. The answer is yes.
Okay.
More terabytes, absolutely. More performance, absolutely. You know, this isn't the trade-off, really. One of the interesting things that's happening today is the advent of what Micron calls 3D NAND, three-dimensional NAND. Again, you may have seen a few weeks ago a joint announcement between Micron and Intel, but to be fair, there are other companies in this technology as well. But 3D NAND is this interesting breakthrough where we are, trying to work around the lithography of NAND. You can only make it so small, otherwise it becomes very difficult. So now let's rise in the Z dimension. So that's going to radically, my opinion now, radically increase the amount of persistent store that you can put in a given area, maybe on a 2.5-inch SSD or on a half-height, half-length PCIe card or on a mobile device, on an M.2 stick, things like that. So certainly capacity is going up. 3D NAND, I think, is the primary driver behind that. But then in the area of performance, guess what? 3D NAND actually has benefits there as well. More channels to the NAND, increased parallelism to the NAND. So the access to the device itself and the larger devices are actually increasing as well, because what you don't want is a very, very slow interface with a gigantic amount of persistent store behind it. That makes little sense in terms of architecture. So that's why it's important for the interfaces to keep progressing and things like transports like NVMe. So performance now can be realized from these relatively large devices. And you're going to see, again, my personal opinion, you're going to see a very, very strong increase in both the capacity and also performance of these devices. And then we get to the most important part about performance, which is now, again, this is chase the bottleneck. So let's go up the host stack and look at the software, particularly the hypervisors, the OSs, and the applications that are actually issuing these IOs, and step back and take a look to say, do we really need to issue that IO? If so, can we make it more efficient? I'd rather issue, to a non-rotating device, I'd rather issue a very large request than a very small request. Why not? I have a very efficient transport in between. I want to fill memory as fast as I can. So that's kind of where Flash is going. And then again, the next step out, non-volatile memories. There's all sorts of different forms being developed. Probably too early for me to comment on a lot of that. But there are lots and lots of papers in the literature about advanced memory techniques, so-called emerging memories, that are, again, I think they're going to change the face of the way we do compute. Because if you think about the concept of a very large non-volatile store accessed in memory semantics at memory speeds or near DRAM speeds, this is going to really have a profound effect on the way we compute. And then you couple that with very fast persistent store, whose price is dropping over time. Again, as the kids would say, this gets interesting in a big hurry.
Great. I think we have time for about one more question. I'm going to change it up a bit here.
Sure.
This one was, so where do privacy and security fit into your future vision?
Where do they fit? Well, Jerry, thank you for the question. I appreciate you being on the webcast. I'll tell you what, they are ever more important. That's kind of why I had the slide on, data as policy. Can we save us from us, right? Privacy and security, I think, need to be redoubled, or at least how we think about it, because of the advent of some of these new technologies. It's cliche but true. You can get to a wrong answer very fast these days. And I think you can become insecure and leak private data very fast these days, perhaps without knowing it. So I think, and again, you talk to the folks, I am certainly not an expert on data security. I know enough to be dangerous about it, but the folks that are, and that I work with very closely, for example, on the SNIA, there are all sorts of A, new interesting techniques, but B, the application of policy by businesses and organizations treating data, and not just data that's currently on your own premises, but data that is off your own premises and, more importantly, on your mobile devices. For example, 5 years from now, it is certainly not infeasible that I could have a terabyte in the palm of my hand. How do you secure that? How do you make sure that there is private data that stays private, but the data that I want to release, I can release it out to the social media or to a friend of mine or to a consumer that might be interested in my data from an analysis point of view. Jerry, I think it's going to be hugely important. We do have to invent some new techniques, I think, especially in the realm of security, to deal with these large data stores, but that is a challenge that I actually relish, and I know the folks that are involved in the security aspects of large data stores relish as well. Again, with the advent of very high-speed networks, literally in the blink of an eye, lots and lots of things can happen. Some of those things might be bad. So we need to step our game up in that area as well and take advantage, to fully answer the question, take advantage of this enormous compute potential to do analytics for the purposes of looking at breaches and looking at potential security violations. Take advantage of all these cores and analyze the streams of data, hopefully in real time, but as close to real time as you can. I think we can do a lot more in that area than we have even just a few years ago.
Great. Hey, thanks, Rob. I think that's that's all the time we have for questions. Rob, I want to thank you for your time today, and hope you'll join us again sometime for another webcast.
You bet. I look forward to it, and I really appreciate all the folks that sat on the webcast. There is the recording, too, as you mentioned before. It's very good to converse with you. I am happy to take questions offline and then do webcasts in the future as well. Thank you very much.
Terrific. Thank you. And in fact, actually, if you want to hear more from Rob, you can follow him on Twitter under the handle of @Peglar. That's @PEGLARR. Or connect with him via LinkedIn. So you can do that directly, or you can click on the Twitter or LinkedIn icons that are in this presentation. And as always, you can also follow all of Micron's flash storage activities, from news to trade show events to industry perspective, by using our Twitter handle @MicronStorage. And just want to thank you again, and we'll be choosing 3 lucky winners from amongst all the registered live webinar viewers today, who will receive, each will get a Crucial MX200 250 gigabyte solid state drive and installation kit. And the winners will be notified individually. And please join us for our next Micron Valued Partner webinar coming up on July 15th, when our own Doug Rollins will be back, his 3rd time now, to share some new research produced by our Micron Storage Lab team that looks at getting better performance and less complexity from Microsoft SQL and Micron's P420M. It'll be a great information for anyone who wants to learn how to accelerate and simplify your SQL workload deployment and leveraging Micron's solid-state storage solutions. So please use the link in the resources guide to sign up for the next webinar. And until then, I'm Matt Wokus, and on behalf of the entire Micron Storage team, thank you for joining us, and have a great afternoon.